All right, so had a discussion over electric field strength, electric fields formula for the field strength F over Q in previous lecture, and we did also discuss what Coulomb's law is. I'm gonna start off from Coulomb's law today. We'll write down the definition once, and then we'll move on to its formula and explanation. So, so Coulomb's law is basically when any 2 point charges exert electrical force on each other. You need to focus on this word point charges. Okay? So it's when any point charges exert an electrical force on each other, and now that force has to be proportional to the product of the charges, all right, and inversely proportional to the square of separation between them. I hope you can draw some parallels between gravitation, Newton's law of gravitation, and the Coulomb's law. F is directly proportional to Q1 product of the charges, and it's inversely proportional to the square of the separation, r square. K is supposed to be a constant. The constant K has a formula of 1 over 4 pi permittivity of free space epsilon E. And permittivity of free space is 8.85 times 10 raised to the power of minus 12 Fm negative 1. So combining these two relationships and including this K, the resulting formula is F is K Q1 Q2 over R square, directly proportional to the product of their charges and inversely proportional to the square of the separation. If you apply this value of epsilon E into this formula, you get a resulting value of K, which I'm just going to write it here for you. You can simply use this value instead of the expanded formula for K, 8.99 times 10 raised to the power of 9. So this is the uh, value of K. Listen, we need to hold up for a second. I'm sorry for the disturbance. We'll have to just hold on for another few minutes. So this 8.99 times 10 to the power of 9 is the value of k. Um, Let me know if you're clear up to this point so we can move forward.
Yes, it's clear.
So let's understand this with the help of a diagram. If let's say this is first charge, which is Q1, and this is the second charge, that is separated by distance r. So this positive sign over here, let's say the formula for this one would be kq1 q over r square. And what if there was a force of attraction between these two charges? One of the charges was, let's say, negative and one was positive, q1, q2. In that case, because you see the charges are being attracted, so the formula is minus k q1 q2 r square. And this negative sign over here shows that the forces are attractive. This negative sign will not be used in the calculation, you should remember that. In such formulas, may that be gravitation or for Coulomb's law, the negative sign just indicates the direction of the forces. Now, electric field strength. I had a discussion of electric field strength yesterday, that electric field strength is force by unit charge. Studying strength, it's force by unit charge. As per the marking scheme definition, electric field strength is the electrostatic force. This is known as electrostatic force per unit charge placed at a point in direction of force. So, um, is equal to, अभी हमने we just studied this formula for F. F is k q1 q2 r square. So what if we
इसमें
simply
सब्स्टिट्यूट
replace?
कर देंगे इसमें.
Yes, we're gonna simply substitute here. So q1 q2 over r square, and this last denominator q original remains as it is. This q will just simply eliminate one of the q's from the formula of force, and the remaining equation is E k q over r square. So yeah, kq over r square. This is another formula for electric field strength. Okay, where there's no need to simply put in force. You can just use one of the charges. You can use the value of k, radius, the separation square, and yeah, that's it. So we've studied two formulas for electric field strength now. So let's further discuss this. E is inversely proportional to the square of radius. E is directly proportional to the charge. Yeah, if the charge increases, the electric field strength will also increase. This is pretty straightforward. Assuming you're placing one charge at any point in space, the greater the charge, maybe it's, let's say, 5q. So 5q will have a greater field around it, and compared to a charge of 2q, would be lesser. The charge 2q will have a lesser field around it. So the greater charge, the greater the field, and greater the radius, lesser the field. That's again pretty straightforward. If you take square of radius and yeah, and as the value increases, the field simply decreases over time because the distance keeps on increasing. And definitely, you're gonna feel more charge if you stay near the charge itself. Sorry, you're gonna feel more the effective field will be greater if you stay near the charge, because that again, the closer you are, the more effect it will have on the object. Graph of E against radius would look something like this. Have I drawn these lines at two quadrants? Because this one shows a graph for a positively charged object, and the second one is for a negatively charged object. I hope this is clear up to this point.
Oh, yes, it's clear.
Okay, now there's another concept of electrical potential, electric potential. Electric potential at a point is basically work done per unit positive charge. So uh, it is work done per unit positive charge by an external force in bringing it from infinity to a point in the electric field. Yani, we're once again assuming, I'm pretty sure you're now clear with the concept of infinity, a 0 point that we assume in space for these values whenever there's a need to calculate work done or electric potential. So you're assuming that this is point zero and you're bringing a charge to, let's say, any point. This is point B. So in order to bring a charge from infinity to any point in space, the work done that the charge the charge possesses, will be the electric potential if you divide it with the positive charge. So V is the symbol for electric potential. It's W over Q, work done over charge. Similarly, you can deduce a formula for electric potential energy as well. Once we've studied potential, we can also understand the concept of electric potential energy. Once again, it's also similar to the differences that we had studied between electric gravitational potential and gravitational potential energy. So electric potential energy has a general formula of U equals Fr. So what is Fr? F is force, R is radius, U is electric potential energy. So now F is Q1 Q2 over R square. So we're going to simply write K Q1 Q2 over R square, where U, we're finding a value for U, and multiplied with R. R and R we're going to just eliminate, K Q1 Q2 over just 1R. So this is the formula for electric potential energy, K Q1 Q2 over R. Is it clear till this point?
Clear.
Yeah. Similarly, if I ask you to, let's say, substitute, because देखो अब हम जरा jump back to electric potential. Potential energy is K Q1 Q2 over R. ये जो W है जो work done होता है, this is also delta E, right? This is also energy. So if this is energy, can we use this newly derived equation of energy in place of this, in place of W over here, and see how the formula will turn out to be? So V is KQ1 Q2 over R divided by Q. Q further eliminated, so you're left with KQ1 over R. This is the formula for electric potential now. A further derived formula for electric potential, right? Why did we do it in at the end? Because we had to first derive a formula for electric potential energy, and then potential energy or positive charge is electric potential. So I mean, this is how we were able to use that formula. Just we need to be very careful with these formulas. You need to remember all of these because most of these formulas are pretty similar to one another. So it's important to just know the difference of
इनकी डेरिवेशन एग्जाम्स में आती है.
डेरिवेशन एग्जाम्स में आ भी सकती है अगर शो दैट वाला क्वेश्चन आए तो. किसी में होता है कि शो दैट हाउ इज v इक्वल टू के क्यू, मतलब ये आ जाएगा हाउ इज v इक्वल टू के क्यू ओवर आर. So you'll have to start from w by q, then you'll be plugging in certain things in this. So, all right, let's try to let's do an example question here. And I'm gonna iterate the question. I'm gonna just write it here so that we'll solve it together. So, for example, the question says that there's an alpha particle that covers a distance of zero point 0.5 times 10 to the power of negative 12 meters. This is the distance that the alpha particle covers. And from a gold nucleus, we're talking about an alpha scattering experiment where there's a gold nucleus. A gold nucleus has a proton number of 79. इसका मतलब ये है कि यहाँ से they're definitely giving you this value for a further calculation है. तो अब लिख लो डेटा क्या है. R हमारे पास given है which is 0.5 times 10 to the power of negative 12. Q is 1.6 times 10 to the power minus 19 times 79. हम ये elementary charge की बात कर रहे हैं. And the question is you need to calculate work done. ये distance move हो रहा है. What is the work done? So work done formula is KQ over R. ये कैसे पता लगा कि हमने KQ over R पे जाना है? क्योंकि they've given you data for radius, they've given you charge, right? लेकिन ये तो potential है, तो potential से आगे फिर हम जा सकते हैं work done पे, right? So let's first of all figure out electric potential and then we'll figure out potential energy. So for work done, what they're essentially asking you is to find delta E, that is electric potential energy. So is 8.99 times 10 raised to the power of 9. Q is 1.6 times 10 raised to the power of minus 19 times 79 because we're talking about the gold nucleus here, and 0.5 times 10 raised to the power of minus 12 is the value for the radius. Can you use your calculator and figure out the answer?
Yes, give me a minute.
It's 2276 7267. So you can simply write it in standard form, 2.7 times 10 to the power of 5. Now this is a value for electric potential. V is W over Q and W is V times Q, where V is 2.7 times 10 to the power of 5. Q is 1.6 times 10 to the power of minus 19 times 9. जो भी आंसर होगा it will be for W, work done, that's it. So you had to solve this question in 2 steps. Remember, we refer to V as voltage, which is work done or charge, and used to refer to V as voltage, but now more correctly you can refer it to as electric potential. So also the concept of infinity that we were discussing earlier, the point of zero, remember zero of potential is the point where a charge has zero potential energy, right? We assume that this is an initiation point and this is where the charge will start to move from. The energy is zero, and now moving further from that particular point, because of the work done, there will be an energy change. All right. Okay, so Let's look at few more concepts. Energy in a radial field. Okay. So a radial field is that. And let's say for our reference, I'm drawing these two radii here. So this is, let's say, point VA. This is also the, okay, this is VP. This is VC. And this is VD. The charge is moving in a circular motion here, okay? And circular motion here there's no work done. I know why. Listen, can you hear me?
Sorry, what did you say? वो actually voice crack कर रही है आपकी
I
बार
was,
बार.
I was asking कि the charge is moving in a circular motion, and for this specific reason, there is no work done on the charge. Why do you think so?
It's not moving in the direction of the force applied.
Exactly, there's no change in radius. So only a radius change will cause work done. So point charge is a hypothetical charge basically, located at a single point in space, and um, so if you move between any two equidistant points, work will not be done, so electric potential will not change. Similarly, why? Because you see, work done is used to separate charge or to overcome the opposition to charge. इसलिए if you're moving between two equidistant points तो work done नहीं होगा, or if you're moving in a circular motion the work will also not be done. So moving between two equidistant points, no work done. Why? Because, and yeah, so the consequence is that electric potential will not change. So let's look at a few graphs here. If E is V by D, or E is V over R, so E is inversely proportional to 1 by R and V is also inversely proportional to 1 by R. So अगर आप यहाँ पे ग्राफ देखो, E on the y-axis, R square यहाँ पे, R यहाँ पे, this is how the graph would look like. Similarly, if you keep V here, R यहाँ पे, R square, R, and this is how the graph would look like. Yeah, so in previous lecture we did also talk about a comparison between gravitational and electric fields. I think we don't need to go over that again. That was it. So let me know if there's any question.
No, there's no question.
Have you started practicing topical papers?
No, मैंने book reading की थी, अभी मैंने papers नहीं किए. I'll do them by this weekend.